color televisions on Earth, okay? Forget about flat screens. So that was a dream. That was science fiction. We had big, bulky televisions in black and white, bad sounds, and big cameras. And so we had to use that technology to go to Mars. And the result was that, yes, we discovered polar caps, but nothing else. And then, obviously, technology advanced very rapidly. And in the next slides, you may see that there was a gigantic step forward with the Viking missions, basically with the analysis of the data that continue into the 80s. So this was something which is still unprecedented. I guess you agree that today, if we are asked together, NASA and ESA, to do the Viking mission today, we would have a big problem in doing it again. So at that time, our colleagues of that time, probably they were kind of a better of us, I must say. It's a kind of embarrassing to say, but it was at the end of the 70s. Two gigantic landers landed softly on Mars. And then they were supported by two big orbiters. And with these devices, what we understood on Mars completely changed. We even saw frost forming on the surface. We saw clouds. We saw fog forming in the canyons. So we understood that Mars, from a meteorological point of view, was a kind of very lively planet. It was not this big rock of sand and craters as we thought 10 years before. And then our understanding of Mars continued to evolve. In the next slide, this is Mars Global Surveyor. This is when really we started to see clear characteristics of water flowing on Mars. The big question is, now we all understand with this mission in the 90s that there was water flowing on Mars. But the big question, and still we are not able to answer this question, is when this water was flowing on Mars. Well, this is a real challenge. And with the advancement of technology, we had more missions. And in the 2000, we're getting close to our age in the next slide. So this is the time when even Europe woke up, and eventually we joined NASA and America in the exploration, and Russia a little bit. They have been not so lucky in going to Mars because they sent lots of spacecraft and they lost them all. So we were really afraid of making mistakes in Europe. We've been thinking and thinking and thinking about making missions to Mars, and eventually we did it. We launched it in 2003. And because now we understood at the time of launch of Mars Express, that is the first European mission to Mars, that water was an important thing, we decided to really design a spacecraft that could monitor what we call the water cycle of Mars. In other words, we wanted to go from the underground to the surface, to the atmosphere, and to what Mars loses continuously towards outer space, and try to understand where the water is coming from, where it goes, and how it disappears. And so this mission is really very focused in understanding the water cycle. But this is also the mission that for the first time measured methane in the atmosphere of Mars. It was a big debate. No, it's a mistake. It's an interpretation error. But eventually, most of the scientific community agreed that Mars Express, with an instrument that is called PSF, discovered for the first time traces of methane on Mars. Does that imply, as Jack said before, that we have cows on Mars having problems with their digestion? I don't think so. Methane can be produced geologically with volcanoes and so on. But the question is, if we can find much more methane, does that discovery have an implication on possible life forms, maybe somewhere in the depth of Mars? We don't know. So that's why we have to go back to Mars. And this time, because the technology and the complexity of the mission is huge, we really need to do it together. I mean, NASA by itself, European Space Agency by itself, we don't have the capability of continuing a major effort of exploration on Mars. So we got to do it together on Mars, and we will do it together at least for the next 20 years. So in the next slide, Oh, that is funny because it tells us how when we start penetrating with these penetrating radars into the surface of Mars, we find out that probably there is a lot of water in the underground of Mars. So the little man now has become a scuba diver, but not on the surface of Mars, in the underground of Mars, okay? So there is where we want to go looking for water and maybe life forms. Why so deep? Because first of all, you need water, and secondly, you need to be protected against the radiation. If you are on the surface, everything gets sterilized and everything dies in a matter of minutes. So if we want to go looking for something that exists, extant life on Mars, we gotta go deep. And so with the next missions, we will try to do that. Next slide, please. Okay, we can skip that because anyhow that's to show how intense is the effort of exploration on Mars. And it will continue even more, we hope, with new budgets. That's the plan, at least, if the politicians allow us to have the budgets to go to Mars. But you never know. Next slide, please. Okay, and now this is in 2016 where really NASA and ESA will work together. We'll be at the same time in orbit and on the surface with two major rovers. And so we're going to search for methane in the atmosphere, and at the same time we'll be able to drill for few meters into the ground of Mars, looking for possible life forms, or maybe looking for sources of methane. So this is a major mission. These two missions will be working together in the 2018-2019 time frame. The orbiter will be launched in 2016. It's under construction in this very moment. And the two rovers, MAX-C and ExoMars, will be launched in 2018 and will arrive to Mars 6 months later. And so this is a major step forward in the exploration of Mars, and maybe we will have answer to these fundamental questions: where the water comes from, is there any life together with the water, is life producing methane, or is just a geological process? But we cannot stop there. And after 2018, we have to continue the exploration on Mars, and we'll continue to do it together. In the next slide, you see what's going to happen after 2018. One major step is a mission where we'll be able to land on Mars, get a sample, half a pound of rocks, and bring them back to the surface of the Earth. Now, you hear often on televisions or on the press or everywhere on internet that we should send astronauts to Mars. For the time being, for us, NASA and ESA, it's a major challenge to go to Mars and return a pound of rocks. Imagine returning hundreds of kilograms of human flesh without killing that human flesh. So that's why I put the question mark. Who knows when we'll be able to send astronauts there? But anyhow, one day we will do it, and it will be a major effort, and maybe is your future work, working on a space mission that will take astronauts to Mars. Thank you.
Thanks, Marcello. So I'm going to pick it back up and talk a little bit about the hardware that allows us to do all these things, to find all these discoveries, to understand these things, and how we get them there, what they can do for us. As I mentioned earlier, the Curiosity rover, otherwise known as the Mars Science Laboratory, which is the overall mission, the rover is called Curiosity, is going at the end of 2011. I'm going to talk mainly about that. It's an excellent example of hardware, and this is, as I said earlier at the introduction, there's a little bit of science, a little bit of engineering, a little bit of everything for folks, so this will be the engineering part. Let's go ahead. So this is what the rover looks like. This is a large rover. Steve mentioned that Spirit and Opportunity are about 300 pounds. This is nearly 2,000 pounds. This is the size of a small car. I'm going to show you some actual footage of it and some images of what goes into making something like this. It looks fairly simple on the outside, but it's actually a pretty impressive engineering feat. What I'd first like to do, however, is run a short movie and introduce you to a gentleman named Dave Gruhl. Dave is the head of the test team at JPL, which is where this is being built, and he's going to take you through a quick, about a minute-and-a-half tour of the assembly process that's going on right now for the Curiosity rover. On your brochures, there's actually a website link, and you can go watch this happen real time on a thing called Curiosity Cam, which I encourage you to do after this. So if you'd roll the video, please.
Hi, My name is Dave Gruhl, and I lead the team responsible for assembling, testing, and launching the next rover to land on the surface of Mars, Curiosity. The team just recently installed a mobility system onto the sides of the rover. That's the wheels. There's 6 wheels, 3 on each side, that all have to be verified that their actuators work. And then there's steering actuators too, which is what we use to actually turn the rover when it's on the surface. There are 10 small little motors that make up that mobility system. And what the team is doing right now is they're going through and making sure that each of those wheels spins forward and backwards and rotates if necessary from a steering point of view, so that when the rover gets down to the surface of Mars, it can successfully navigate itself over the rocks and the terrain that are actually there on the surface. As soon as we finish up the mobility checkout, they'll be putting the mast on the top deck of the rover, and the mast is more cameras and imaging that allows it to take stereo pictures off in the distance of Mars. Just like your eyes work in a stereo pair, this camera will also return us stereo imagery from the surface of Mars. Once that's complete, then the front deck of the rover, which is empty right now, is where we'll put the robotic arm. The robotic arm is a device that reaches out 6 feet or so and actually touches the surface, takes samples, and then deposits those samples back into the innards of the rover for the science instruments to analyze and determine what the elemental compositions are of the surface of Mars. Over here on my left, you'll see the descent stage. The descent stage just went through a test where they actually shook it, just like it would experience when it's out going through the launch. And they wanted to make sure that the design held together and then nothing broke, and everything was successful with that test too. This has been your update on the assembly of the Curiosity vehicle. As you can see, Curiosity is looking more and more like a rover every day, and the team is working hard as we aim for our launch scheduled for November of 2011.
Okay, so if we go to the next slide, please. So you saw a little bit of an animation of it. You've seen it from a distance. Now let's kind of get up close and personal with some of the hardware here on the Mars Science Laboratory. So this is what it looks like. You'll see that in that masthead, there's not only the eyes, but there's a thing called chemistry camera, which is really cool. I hope we can get sound effects from it. You'll actually see it in a little bit in another animation. But it's got a laser in it, so it stands off, and 20 feet away, it can zap that laser at a rock, create a plasma from that rock, and then analyze what's in that and decide whether it's worth driving over there to look at it. The main REMS is actually an instrument that provides meteorological data, wind speed, pressure, temperature, things like that. We had a question earlier about meteorology. We're going to measure it directly. Just like we had a question about radiation. There's an instrument on here called RAD that measures the radiation at the surface of the planet. So we will get our first really good solid data set for that. And then inside is really where the hardest working and the most complicated instruments are. And essentially we've taken a chemistry laboratory and we've squished it down into a couple of small boxes, stuck it in